Okay, so in the next couple of videos, let's start doing some proofs. They are just well, some are proofs, some are gonna be like meta theorems in the sense that they are kind of like whole families of theorems that we can apply later, and they can be useful for other proofs or to get to understand better this syntactical implication. So let's start with this one. So in this case, we have P is a relation symbol, and that belongs to our vocabulary tau, a unary relation symbol. And we want to show this formula up here. So this is what we're going to do. So this is essentially the contrapositive of for every y not p of y implies not p of x, which this belongs to group 2 of the axioms. Let's just write it down. Group 2 of the axioms is the one that says for every x, in this case is a y, for every y alpha implies alpha, replacing y by t. So remember, in group 2, what the variables are, x, y, doesn't matter. I guess when we wrote it, it was an x, but we can use any variable we want. This is just a variable, y. And this, remember, this means replace every occurrence of y by t. So here, this is t, and this is alpha. And this thing up here is alpha, where y is being replaced by t, right? So, okay, so that's our first thing in the deduction. Then the next one is gonna be, this one up here, which is part of the axiom group 1. Axiom group 1 is the axiom group that represents tautologies. And this one up here is essentially a tautology, the one that says that if A implies not B, then B implies not A. Right? That's a tautology. You can check that that's always true in sentential logic. And of course, this is being A up here, and then this one is A up here. This one is B. This one is B without the not. The not is outside. So that's a tautology. And now, if we see, our deduction has two formulas, the ones in black. And now we can use modus ponens and get the one we want, right? Because if you notice, this one up here is the same as this one up here. So modus ponens is going to give us now that p of x implies that for every y not p of y. And this is by modus ponens. Okay, so that's exactly what we want. Well, because this exists, remember, is just a shorthand for this formula up here. Okay, so that's a deduction. It has 3 lines, and that's how you use that simple implication. By the way, there is no gamma here. So essentially what we are doing here is we are thinking of there is a gamma here where gamma is the empty set. Okay, so if you don't write anything, it is the same thing as assuming the empty set. The gamma is the empty set. Okay, so, and this doesn't need any assumption. This is a theorem that you can prove without any assumption. It just follows from the logical rules, essentially, the logical axioms and the modus ponens rule. Let's do one more, a bit more interesting. And this one is very similar to the other, except that it has a for all up front. And the thing is, we don't have any rule that allows us to put a for all up front. We have one right in here, essentially, that allows us to put a for all up front. But that one requires x not to be free in alpha. While what we want to show here, if this is your alpha, x is free there. So we cannot put it there. But this still works in this case. And the proof is going to be a bit longer than the one we had today. But the idea is as follows. This one here is the proof we had today. And it's not a proof of what we want because we want the for all. So we have to change it a little bit. So this part up here, we're going to put a for all x up front. Remember that the axioms, we're allowed to generalize with all the formulas I had in that listing, right? So we're talking about generalizations. of all these things, right? So we can, generalization meant you put the for alls up front, right? That's what it meant. So here we can put the for alls up front. And this one right here, we can also put the for all up front for every x, and then that implies all of these. Now, okay, that's because we are trying to reach this for all x right there. But now we cannot use modus ponens, right? Because modus ponens, you need to have something of the form alpha, and alpha implies beta. Yes, so that's not what we have right here, because we have the for all up front, right? We don't have this one. This is not, oh, this is of the form for every x, alpha implies beta. But that's, and this is of the form for every x alpha. But that's not what we want, right? We want clean alpha implies beta and alpha. So this has the for every x in front. So it's not what we want. But there is this axiom up here that says that if you have for every x alpha implies beta, you can obtain for every x alpha implies for every x beta. So let's do that. So the axiom says that thing. So I'm going to be lazy, and I'm going to call this alpha, and I'm going to call this beta. Okay, so then we have an axiom that says for every x alpha implies beta implies for every x alpha implies for every x beta, right? Now, this thing up here is exactly this thing up here, right? So we can apply modus ponens to that and get for every x alpha implies for every x beta. Now, what is alpha? Alpha is right up here. This is for every x alpha, right? And here we have modus ponens. So what we can deduce is that for every x beta. And now that is right here. This is beta. Okay, so what I'm saying is that we have for every x alpha implies for every x beta. We do have for every x alpha, so we can obtain for every x beta for this particular beta. And that is exactly what we want up here, right? So this formula is the same as this formula up here. So now we got a sequence. Our deduction sequence has 5 steps, which is fine. We can have it. Any finite number is okay. But we needed a few more to put the for all up front. Okay, good. So that's how you prove that. Now, let's prove a generalization of that. It's called the generalization theorem, which generalizes not only that, but it generalizes more. It says that if you can prove a phi from gamma, and x is not a free variable in gamma, in any of the formulas that show up in gamma, then gamma can prove for every x phi. Okay? It kind of makes sense, right? Because essentially what this is saying is that if you can prove something about x, suppose x shows up in phi, but it doesn't show up in gamma. And you can prove something about x, but without any assumption about x, because x doesn't show up in gamma at all. So we are not using any assumption about x, and we are still be able to prove something about x. So that means we should be able to prove it for every x. That's the intuition behind what's going on here, but that's not the intuition behind the proof. The proof is going to be a syntactical proof of why this is the case, because so far for us there is no intuition or no meaning to this guy. It's just purely formal. So to prove this, we just need to use the syntax. The proof is by the induction principle. And the induction principle said that if you have a set S that is closed under modus ponens and that contains the assumptions and the axioms, then it contains every theorem. So let's prove that this is true. This is true for every theorem. Okay, so let S be the set of all phi such that gamma proves for every x phi, and let's prove that is closed and contains gamma and lambda. So first, gamma subset of S. Why is that? Well, if phi belongs to gamma, we can have the following deduction. Phi, which belongs because it belongs to gamma, and then we have the formula phi implies for every x phi, which is group 4, and we can use this because x doesn't occur free in alpha, right? So here, since x doesn't occur free in gamma, it doesn't occur free in there, so that's group 3 axiom. And then we apply modus ponens and we get that for every x phi. So that's a deduction of, therefore gamma proves for every x phi, and phi belongs to S. Okay, so what is that lambda is a subset of S? That's because if we have an axiom that belongs to S, we can include all generalizations, right? So the axioms, we can always put a for all in front of an axiom and we still get an axiom, right? So all the generalizations of any axioms are still axioms. So essentially what I'm saying here is that if phi is in gamma, then for every x phi is also in gamma, and therefore what I'm saying here is that if phi is in lambda, then for every x phi is also in lambda, so it's also a logical axiom because it's a generalization of phi, and therefore we get that gamma proves for every x phi. The deduction is a one-line deduction because you already have an axiom. Okay, so we also get phi belongs to S. And then last, we need to show that S is closed under modus ponens. So how do we start that? So suppose that we have alpha and beta that belong to S, right? So that means that we have two deductions. The gamma proves for every x alpha and gamma proves for every x beta. Suppose that alpha and alpha implies beta belong to S. So that means that we have two deductions, one that gamma shows for every x alpha and another one that shows that for every x alpha implies beta. Okay? So now we want to show a deduction of, we want to show that beta is in S, so we want to show a deduction of for every x beta. Okay, so essentially what we have so far is we have a deduction, alpha 0, alpha k, that ends in alpha. This is a deduction. And then we have another deduction, gamma 0, gamma L, that ends in for every. So far what we have is a deduction, let's call it phi 0, phi k, that ends in for every x alpha, because we have a deduction of this. And then we have a deduction psi 0, psi L, that ends in for every x alpha implies beta. And we want to continue, so these are the two deductions that we have. We can put them one after the other because they are all, this is still a valid deduction because the rules still apply. And now we want to continue to end up with a reduction of for every x alpha implies beta. So how do we continue this one? Let's continue in here on a side. So we're going to continue, we have to use this formula that we have. For every x alpha implies beta implies for every x alpha implies for every x beta. That's a group 3 axiom. And then an application of modus ponens between this one and this one, we get for every x alpha implies for every x beta. And now an application of modus ponens with this one and this one, we get for every x beta. Right? And this is a deduction of beta. So we have shown that gamma implies, syntactically implies for every x beta, and therefore beta belongs to S. So this shows that S is closed under modus ponens and contains gamma and delta. Therefore, S contains all theorems of gamma. So that means that that's what we wanted. So we show that for every phi that is a theorem of gamma, phi belongs to S. So that proves that. So that's how we get that. So notice this proof. Notice this proof gives us a transformation essentially of a proof of this into a proof of that. But it's not a direct transformation in the sense that we just add things at the end, because we are using the induction essentially. This is so we have kind of from phi, like in the case when phi is alpha implies beta, we kind of have a deduction of alpha. I guess that should be a theorem, but we have to get a deduction of for every x alpha, and that's kind of in here. So there is the induction. So these rules here are being applied by induction every time there is a modus ponens. So every time there is a modus ponens, we're adding like 3-4 lines in the middle of our proof. And in this case, we are applying these ones every time we use an assumption, and we are applying generalization. We're changing the logical axiom in this case. So we're kind of changing the whole proof to go from a proof of this to a proof of that. So it's quite interesting that it's not just adding more things, but it's changing the whole proof, but it still works. Okay, so this is very useful when you want to prove something, because it kind of cleans up a bit your proofs, because now you can just prove something without the quantifiers up front, and you can add them at the end. Okay, we'll see more meta theorems in the next video.